We will now discuss approximation properties. For LP spaces. Okay, so by this I mean identifying sets which are dense and also some separability properties of LP spaces. So we are dealing with omega in Rn, open set, equipped with the Lebesgue measure. So this is the measure we are going to talk of, and then I said the notation for this is LP of omega 1 less than or equal to p less than or equal to infinity. Okay, so we are going to define a set S which is equal to set of all phi from omega to r, phi simple, vanishing outside a set of finite measure. That means if you write phi is sigma alpha I chi of ei, where alpha I are all non-zero, then the union of the chi I will have finite measure. Okay, so if 1 less than or equal to p less than infinity, then phi in S, then phi simple, then phi is in S if and only if phi is in LP of omega. Because you are having it is vanishing outside a set of finite measure. So if it is in LP, then it has to be integrable. Then where it is non-zero, it has to be of finite measure, of course. And conversely, if you have a set which is 0 on a set of finite measure, then it will be a simple function, because all the alpha i's are going to be positive on the real numbers. Okay, so lemma. Omega in Rn open set, 1 less than or equal to p strictly less than infinity, then S is dense in LP of omega. That means every function in LP of omega can be approximated as closely as you like by means of function which is in S. So f in LP of omega 1 less than or equal to p less than infinity, and f, let us say, non-negative. Then there exists phi n which increases to f, phi n greater than or equal to 0, simple. And since phi n increases to f, so phi n is less than or equal to f, this implies that phi n is in LP, and therefore that implies that phi n is also in S. Now what about phi n minus f power p? This is less than or equal to 2 power p mod f power p, and this is integrable. Then phi n minus f power p goes to 0 pointwise. Therefore, by the dominated convergence theorem, we have that integral mod phi n minus f power p dmn omega. This goes to 0, that is phi n goes to f in LP of omega. Okay, so now, every element f which is non-negative can be approximated by means of functions which are in S. Now if f is in LP of omega, you write f equals f plus minus f minus, then f plus minus are in LP of omega and they are non-negative. Therefore there exists a phi n in S and a sequence Cn in S such that phi n converges to f plus, psi n converges to f minus in LP of omega. Then phi n minus psi n also belongs to S, and this and phi n minus psi n goes to F in LP of omega. So this shows that S is dense in LP of omega. Another lemma. Omega contained in Rn, non-empty open set. Of course, I should have said that earlier also. Non-empty, and whether I say it or not, it is non-empty always. One less than or equal to p less than infinity. F is in S. Then it's in LP, of course. Then F can be approximated by step functions in LP of. So what is a step function? Step function is a simple function where the chi of EI's are all boxes. Okay, so remember that. So proof. Okay, so E in omega, set of finite measure. Then we have seen, given epsilon positive, there exists a F contained in omega, F a box, not a box, sorry, a finite disjoint union of boxes such that measure of E delta F can be made less than epsilon. I will take epsilon power p in this case. Okay. Now if you take chi E minus chi F, chi F is a step function. So chi F is a step function. Now chi E minus chi F is going to be 1 or minus 1 on E delta F. It will be 0 everywhere else, and therefore norm of chi E minus chi F power p whole power p is nothing but mn of E delta F, and that is less than epsilon power p. Therefore norm of chi E minus chi F in LP is less than epsilon. So if you have a function E, then so now let F is equal to sigma I equals 1 to n let me take j equals 1 to k alpha j chi ei chi ej, where alpha j in R not 0 and Ej mutually disjoint of finite measure. Then for every 1 less than or equal to j less than or equal to k, there exists Fj finite disjoint union of boxes Fj in omega and chi Ej minus chi Fj in LP can be made as small as I like. So I am going to take it less than epsilon by k times mod alpha j. Okay. Now you set phi equal to sigma j equals 1 to k alpha j chi of fj. So this is a step function, and by triangle inequality f minus phi in LP is less than epsilon, triangle inequality. Okay, so this completes the proof. So every S can be, every element of S can be approximated by a step function. So now we have an important, very important theorem. Okay, so omega in Rn non-empty open set 1 less than equal to p strictly less than infinity, Cc omega equals set of continuous functions with compact support contained in omega. Then Cc of omega, this is of course a continuous function with compact support, so it's non-zero outside the set of compact support. Compact sets have finite measure, and it's bounded on the compact set, and consequently it's in any LP, and therefore Cc omega is dense in LP of omega. So every member of LP of omega 1 less than p strictly less than infinity can be approximated by means of continuous functions with compact support. This is a very useful fact and very important. So okay, proof. So by preceding lemmas, S and step functions are dense in LP of omega, because every member of LP can be approximated member of S. Every member of S can be approximated by a step function, and therefore these are all dense in it. So we can assume to show that, so sufficient to show every step function can be approximated in LP of omega by functions from Cc of omega. So you are given a step function, and so let epsilon be greater than or equal to greater than 0. Then we know, given a step function, we have already shown that there exists a continuous function with compact support. So phi f step function in omega. Then there exists phi in Cc of omega such that the following two properties are true. Norm phi infinity is less than or equal to norm f infinity, and the measure of the set of all x in omega such that phi x is not equal to fx can be made length any small number. So I am going to take epsilon by 2 times norm f infinity whole power p. Then norm phi minus f p whole power p, this is nothing but mod phi minus f power p over omega dmn, okay, and that is less than or equal to 2 times norm f infinity and then mn of, let me call this set E, mn of E. So 2 power p norm f infinity power p, and that is precisely given less than epsilon power p by our choice mn, by the choice of mn. Okay, and therefore this implies that norm phi minus f in LP is less than epsilon, and that proves that every step function can be approximated to infinite function of compact support. So you take a LP function, approximate by a function in S, take the S function, approximate it by a step function. Step function can be approximated by a C infinity function with compact support, and therefore every element in LP 1 less than P less than infinity can be approximated by a continuous function with compact support. Okay, so above result, so remark, not true for p equals infinity. In fact, closure of Cc of omega in L infinity norm is C0 of omega equals continuous functions which vanish at infinity. That means, given epsilon, there exists k compact contained in omega such that mod f is less than epsilon mod fx for all x in omega minus k. Okay, so such functions are functions which vanish at infinity, and that's again a continuous function, and therefore you cannot approximate L infinity functions by means of this. So there are several interesting applications which of this result. We will see them subsequently, but to start with, so we have the following proposition. Okay, so omega in Rn non-empty open set 1 less or equal to p less than infinity, then Lp of omega is separable. Separable means there exists a countable dense set. Okay, so proof. There exists Kn increasing sequence of compact sets in omega such that Kn increases to omega. That means omega is the union of all the Kns. Okay, and now f in Lp of omega implies there exists phi in Cc of omega approximating f. Okay, you can make it as close to it as possible. Then support of phi is compact, and therefore it should be contained in Kn for some n, because Kns are increasing compact sets and they ultimately exhaust all of it. Okay, now by Weierstrass approximation theorem, we can approximate phi uniformly by a sequence of polynomials. And since the coefficients of the polynomials are real numbers, so you can approximate it by rational numbers, and therefore it implies uniformly by a sequence of polynomials with rational coefficients. But Kn is compact on Kn. Yes. Kn is compact implies finite measure, and therefore since L infinity is continuously embedded in any LP, this implies phi can be approximated by polynomials with rational coefficients in LP norm. Now, set of all polynomials with rational coefficients is countable. So, let us say, so Pmn m equals 1 to infinity are all polynomials in Kn with rational coefficients. So, Pmn tilde m equals 1 to infinity extended by 0 outside Kn. Then union n equals 1 to infinity, union m equals 1 to infinity, Pmn is countable and dense in LP of omega. Because given any f in LP, you can approximate it by C continuous function with compact support, and each continuous function with compact support, the support will be in some Kn, and they can be approximated in the LP norm by the PMNs, and therefore phi can itself be approximated by Pmn tilde in all of omega, because outside omega Kn both phi and Pmn are 0. Okay, so you have this, and this shows that LP is separable. You have a countable dense set. So proposition omega in Rn non-empty open set L infinity of omega is not separable. Proof. So let x belong to omega, then there exists a ball center x, radius rx, which is contained in omega. So rx is positive. This is a ball center x, radius rx. Okay, so let us take phi x equals chi of b x rx. So this is a function phi of x. Now let x not equal to y. Then if you take phi x minus phi y, so these are difference of two characteristic functions. On the intersection there will be 0, outside it will be plus 1 or minus 1 or 0 depending where you are, and therefore this norm infinity is always equal to 1 if x is not equal to y. So now you take u sub x, this set of all f in L infinity of omega such that norm f minus phi x L infinity, let's say, is less than 1 by 4. Even 1 by 2 is enough. Okay. Then ux intersection uy is empty for all x not equal to y, because phi x minus phi a is 1, so you cannot have a common element by the triangle inequality. Therefore, set of all ux x in omega is an uncountable set, uncountable collection of disjoint open sets. Okay. Now, so given any countable set, Ux must intersect every one of them, or rather if it is dense, must intersect every Ux. But every element can belong to at most one Ux, because it cannot belong to more than one, because Ux intersection Uy is empty when x is not equal to y. This implies that so this is a contradiction, okay, because you have only a countable number of ones, which will be, so there will be uncountable number which are not intersecting. So this implies that no countable set can be dense, and therefore L infinity is not separable. Okay, it's a very useful idea to prove non-separability. If you can show that you have an uncountable collection of open sets which are all mutually disjoint, then such a space can never be countable. Okay, so we will continue with the applications next time.